April 1943, inspection shift, I saw grit in the taper. One adapter log entry scoring stamped for clearance. My order was filed, the test round misfired. The report was sealed that night. In 1941, British anti-tank doctrine changed. German armour thickness rose faster than British guns. The Ordnance QF 2-pounder was common. It fired a 40mm projectile. It lacked an effective high-explosive shell. It relied on armour, piercing, shot only. In France, it was adequate against early panzers. In North Africa, it met thicker frontal plates. New German models appeared in growing numbers. Longer range engagements became more common. Angled plates reduced simple penetration estimates. British crews faced sharp ammunition expenditure limits. Replacement guns arrived slower than battlefield losses. Their factories were already committed to other programs. New carriages demanded steel, labour, and machine time. The War Office sought interim technical fixes. One goal was improved penetration from existing mounts. Another goal was minimal retraining for crews. The 2-pounder still sat in many turrets. Armoured cars used it for reconnaissance firepower. Some tanks still carried it during 1942. An upgrade had to fit those vehicles. A complete gun swap often required new turrets. That meant drawings, jigs, and production delays. The enemy did not pause for British schedules. Reports described 2-pounder rounds bouncing at range. Crews aimed for flanks when possible. That depended on manoeuvre and terrain. Reconnaissance units could not always choose angles. They needed a frontally credible threat. Britain also faced tungsten supply constraints. The tungsten was critical for machine tools. It was also critical for hard penetrator cores. Competing demands forced difficult allocation decisions. Any solution had to justify scarce materials. Simple velocity increases were most attractive. Higher velocity improved penetration for similar cores. Barrel length changes were limited by mounts. Propellant changes risked unsafe chamber pressure limits. A different concept gained attention in trials. It used a tapered bore at the muzzle. The projectile would be squeezed smaller in flight. Squeezing reduced frontal area at impact. Velocity rose because gas acted longer. Such systems existed in continental experiments. They demanded special ammunition and precision bores. Britain could not retool whole gun lines. Engineers looked for a bolt-on variant. A screw-on adapter promised that shortcut. And it could convert an old gun quickly. It also allowed removal when desired. Procurement memos emphasized speed over elegance. Field units wanted any advantage, however limited. That pressure shaped the Littlejohn adaptor project. Contemporary accounts credit a Czech designer for it. He was a Czech engineer in British service. His anglicised working nickname became Littlejohn in Britain. He proposed a tapered muzzle extension for trials, the extension attached to the 2-pounder muzzle. It used existing barrel threads or collars. That avoided altering the main barrel forging. Early paperwork treated it as an expedient modification. The Ordnance Board required proof of safety margins. Proof loads were fired before troop issue. Design drawings specified a hardened steel taper cone. Internal finish tolerances were tight for wartime shops. The taper had to be concentric with the bore. Any eccentricity would strip the projectile skirt. That could cause erratic dispersion under test conditions. It could also raise dangerous pressure spikes. Tooling had to produce consistent internal geometry. Gauge sets were issued for inspection. The adapter length was short compared to the barrel. Short length reduced weight overhang on mounts. It also limited leverage stress on the muzzle. Even so, recoil loads required careful calculation. The adapter also needed a locking method. Threads alone could loosen under repeated firing. Some designs used locking rings or pins. Workshops debated the best field-maintainable approach. The British manufacturing base was already strained. Many precision lathes were assigned to aircraft parts. As a result, production quantities stayed modest. The adapter was prioritised for vehicle-mounted guns. Those crews faced close-range armour threats. Towed 2-pounders were being withdrawn sooner. The adapter was therefore a stopgap for certain roles. Parallel work created a specialised projectile family. Standard 40mm shot could not be used. The projectile needed a collapsible outer skirt. It also needed a hard inner core. Tungsten carbide was preferred for that core. The outer body was often light alloy. It carried the rifling engagement before the taper. During squeezing, the skirt reduced to 30mm. That produced a smaller diameter penetrator at exit. Ammunition factories had to add new assembly steps. quality control was stricter than normal shot. Core alignment mattered greatly for practical accuracy. Skirt hardness mattered for consistent collapse. Propellant charges were adjusted for the new shot. Trials were run at proof ranges in Britain. Range staff measured muzzle velocity changes. They also recorded pressure signs and barrel wear. Initial results showed impressive velocity gains. They also showed rapid erosion inside the adapter. Engineers modified heat treatment specifications after early cracking. They also modified surface finishes to reduce galling. Further tests examined dispersion patterns at range. Under tight tolerances, the new shot stayed accurate. It was inaccurate when skirts collapsed unevenly. That drove tighter acceptance standards at inspection benches. Acceptance standards reduced output rate in every factory. Supply planners warned about limited issue quantities. War Office staff still approved limited field trials. To official nomenclature called it the Littlejohn adapter. Ammunition was informally called Littlejohn shot. Distribution went first to selected reconnaissance regiments. Vehicle workshops received fitting and care instructions. Those instructions stressed cleanliness and inspection. They also stressed careful ammunition segregation. Mixing rounds could damage the adapter badly. Mechanically, the adapter was a conical choke tube. It created a short tapered bore section. The taper reduced diameter from 40 to 30. Internally, the taper reduced diameter from 40 to 30. This reduction occurred over only a few inches. Rifling existed in the normal bore section. Inside, the adapter itself was smooth without rifling. Squeezing relied on the projectile skirt material. Each projectile entered at 40mm diameter. A gas pressure pushed it into the floor. During travel, the skirt collapsed inward under compression. Meanwhile, the inner core stayed rigid during collapse. At exit, the core was now 30mm. After exit, the sabot-like skirt separated quickly. Aerodynamic drag stripped the lighter outer portion. Only the core continued as the penetrator. This is an early APCR type mechanism. Penetration depended on core hardness and velocity. Velocity increase came from reduced bore area. Gas pressure acted on a reducing cross-section. That effectively accelerated the shot more. Measured velocities varied between ammunition lots. Figures around 1,000 meters per second appear. Standard 2-pounder shot was far slower. This gain translated to better short-range penetration. Penetration numbers were recorded at given obliquity. The results depended on target plate hardness. Results also depended on impact yaw. Notably, the adapter did not change the gun breech. It did not change the recoil system either. It added weight at the muzzle. That affected balance on some mounts. Turret elevation gears felt slightly heavier. Crew drills adjusted for that resistance. The adapter reduced muzzle blast dispersion slightly. It also altered flash signature patterns. Those changes were not the main concern. The main concern was pressure and wear. Squeeze bores can increase peak pressures. British trials monitored primer flattening signs. They monitored case head expansion as well. They required safe operation without structural change. The special shot used a different case marking. Boxes were stenciled for strict segregation. So a misloading standard shot through the adapter was dangerous. A full diameter shot could seize in the taper. That could burst the adapter or barrel. Instructions mandated adapter removal for normal firing. Removal required time and clean working space. Field conditions rarely provided ideal cleanliness. Threads could be fouled by sand or mud. A fouled thread could cross-bind under torque. That could lock the adapter in place. Locked adapters required workshop tools for removal. The adapter material was high-strength steel. Heat treatment balanced hardness with toughness. Too hard meant brittle cracking under shock. Too soft meant rapid erosion and scoring. Erosion occurred where the skirt rubbed. Scoring also occurred from small grit particles. Once scored, the skirt collapse became uneven. Uneven collapse produced poor accuracy at combat ranges. Accuracy complaints often traced to worn adapters. Wear also changed internal taper dimensions. That changed exit diameter and velocity. Velocity spread increased measurably with adapter wear. Higher spread reduced predictability of penetration. Units therefore tracked adapter round counts. Some units marked adapters with punch counts. Others kept log sheets in vehicle books. Log keeping depended on disciplined commanders. Ammunition also had unique storage constraints. Tungsten core rounds were theft targets. They were also scarce, so issue was limited. Limited issue meant crews trained with dummy rounds. Dummy rounds did not replicate collapse behavior. Live firing was rationed to conserve cores, therefore crew confidence levels varied widely by troop. And the projectile skirt often used aluminum alloy. Alloy choice affected collapse and separation. Soft alloy collapsed well but stripped rifling. Hard alloy gripped rifling but resisted collapse. Manufacturers adjusted tempering and annealing steps. Each step required inspection with simple gauges. The core was usually tungsten carbide. It had high density and hardness. It was machined to tight length tolerances. Any core tilt caused off-axis impact. Off-axis impact reduced penetration markedly. Core tilt could occur from poor assembly. Assembly used swaging and crimping operations. Swaging presses needed consistent force settings. Wartime plants varied in machine condition. As a result, lot-to-lot variation existed. Lot variation forced conservative firing tables. Gunners were warned not to trust maximum claims. The adapter also influenced bore cleaning routines. Normal bore brushes did not reach the taper properly. Special scrapers were issued for the cone. Solvents were limited, so oil was common. Oil attracted grit in desert environments. That increased scoring risk during insertion. Some instructions advise firing a blank clearing shot. Blank shots were not always available. Some crews used cloth patches on rods. That could leave fibers in the taper. Fibers could burn and leave residue. Residue changed friction characteristics inside the narrow cone. Friction change could change collapse timing. That again affected accuracy and pressure. Technical notes warned against improvised cleaning. Nevertheless, field improvisation was common during long moves. The gun sights remained calibrated for normal shot. Her Littlejohn shot had flatter trajectory than standard OP. Therefore, sight settings became approximate on issued scales. Some units applied temporary range tables. Others used trial rounds to bracket targets that wasted scarce ammunition during hurried ranging drills. The adapter offered best effect under 500 yards. Beyond that, dispersion and core energy dropped. The core was light compared to full-bore shot. Light cores lost velocity quickly in air. Thus, long-range performance was inconsistent. The adapter was not useful for HE tasks. The 2-pounder already lacked HE rounds. Therefore, the vehicle still needed other weapons. Some vehicles carried a baser machine gun. That handled soft targets and suppression. Against armour, the adapter gave a narrow window. It was a technical trick, not a new doctrine. And its reliability depended on careful ammunition handling. Its effectiveness depended on tungsten availability. Those constraints shaped its real combat value. Field issue began during the later Desert War. Reconnaissance regiments received limited quantities through controlled issue. Many adapters went to Daimler armoured cars. Those cars carried the 2-pounder in turrets. Crews were trained on fitting procedure. They practiced threading the adapter without cross-binding. They practiced removing it after firing. They also practiced segregating ammunition stowage. Stowage racks were labelled by chalk or paint. Labels wore off under heat and dust. Crews tied cloth tags to boxes. The tactical use was selective engagement. Crews saved Littlejohn rounds for confirmed armour. They avoided wasting them on half-tracks. They also avoided firing through heavy dust screens. Dust could enter the taper during an engagement. In action, time pressure reduced procedural discipline. Some reports mention rushed adapter installation. Rushed installation could leave a loose seating. A loose adapter could shift under recoil. Shift caused accuracy loss or thread damage. When threads damaged, the gun reverted to normal shot. Normal shot was often ineffective by 1943 standards. In Italy, armoured cars met close ambush threats. German self-propelled guns guarded road junctions. Reconnaissance crews sometimes had to fight through. Littlejohn shot could penetrate some side armour plates. It could also defeat light armoured cars. Against heavier tanks, it remained marginal. Reports describe crews aiming for vision ports. They also aimed for track assemblies. That those targets required steady platforms and careful lead. Armoured cars were not also stable firing bases. Therefore, hit probability was limited in moving fights. In northwest Europe, reconnaissance units encountered Panzerfaust teams. The adapter did not address that threat. It addressed occasional armoured counterattacks against thin screening forces. In bocage, engagement ranges were short. Short range favoured the squeeze-bore concept. However, mud increased thread fouling on muzzle fittings. Mud also increased cleaning burden after each contact. Ammunition supply lines were complex across multiple depots. Littlejohn shot was incompatible with other guns. Supply depots had to stock separate pallets. Clark sometimes misissued cartons to wrong units. Wrong issue created wasted transport capacity. The units with adapters sometimes received normal shot only. That made the adapter pointless in that period. When correct rounds arrived, they were rationed. Rationing limited familiarization firing for most new crews. Training schools reported confusion about sighting. Some crews treated the rounds as emergency only. Emergency only use reduced tactical experimentation. After-action notes describe occasional effective kills. They also describe frequent partial penetrations. Partial penetration could still wound crew. It could also disable optics and controls. Institutional summaries counted those as limited success. Another issue was adapter wear during campaigns. A worn adapter reduced accuracy in combat. Replacement adapters were not always available. Workshops could not easily ream the taper. Once worn, the part was scrapped. Scrap rates were higher than expected. That reduced sustained operational availability during extended patrol cycles. Some commanders ordered adapters reserved for patrol leaders. That concentrated capability in few vehicles. Concentration simplified ammunition distribution during convoy resupply runs. It also created unequal firepower across troops. German intelligence sometimes recovered unusual shot fragments. Fragments showed a small tungsten core. That suggested a squeezebore or APCR round. Countermeasures were limited by late war realities. Armour could not be changed rapidly at front. Tactics emphasised standoff weapons instead. For British crews, the adapter remained a niche tool. It was used when conditions matched its narrow strengths. Internal reports noted mixed crew confidence. Some crews trusted the higher velocity concept, and others distrusted the special ammunition consistence. Reluctance increased after misfire incidents reported in diaries. Misfires were often linked to damaged skirts. Damaged skirts came from rough handling in stowage. Therefore, commanders enforced careful packing drills. Enforcement competed with operational tempo demands. HQ evaluations framed the adapter as interim. They stressed it could not replace the 6-pounder. They also stressed it consumed scarce tungsten. Tungsten allocations were audited across ministries. Ammunition managers compared benefit per kilogram tungsten. They preferred larger guns using similar cores. The adapter program therefore faced bureaucratic resistance. Resistance grew as 6-pounder output increased. Resistance also grew as 17-pounder plans matured. Some memos questioned training burden for a niche round. Others questioned maintenance burden on vehicle units. Supply officers disliked unique packaging requirements. They also disliked potential dangerous misissue. Operational commanders valued any marginal advantage. They requested continued issue for reconnaissance units. The resulting compromise was limited production. Limited production kept the system from scaling. The enemy response was mostly indirect. German crews already assumed 2-pounders were weak. Unexpected penetrations created local caution in some German crews. Such caution did not change strategic deployment. Strategic effect remained minor compared to new guns. Nevertheless, the adapter illustrated wartime engineering pressure. It showed preference for quick bolt-on solutions. And it also showed limits imposed by supply chains. By 1944, the 2-pounder was largely obsolete. Vehicles were rearmed with 6-pounder weapons. Some were rearmed with 75mm guns. Reconnaissance roles shifted towards speed and radios. Anti-tank tasks shifted to dedicated troops. As rearmament progressed, adapter demand declined. Ammunition factories prioritized other tungsten rounds. Remaining adapters stayed in service where installed. Post-war summaries treated the idea as ingenious. They also treated it as logistically awkward. The Gerlich principle was not widely adopted after. A PDS and shaped charge rounds offered better paths. Those rounds used standard bores without adapters. Therefore, the squeeze bore extension became a wartime dead end. Surviving adapters became museum curiosities and private collector pieces. Collectors value them for their practical audacity. It remains a bolt-on attempt at relevance. Littlejohn adapter made an old gun hurt armour again.